14 of the most powerful AI models in existence were given a single job to read a C program and say yes or no to a bug. We're talking GPT, Claude, DeepSeek, Qwen, Mistral. Not fix it, not explain it, just yes or no. And well, you're going to want to hear what happened.
See, every single model was great at saying, yep, it's fine, but 4 of them, including massive models with hundreds of billions of parameters, correctly identified actual bugs less than half the time. Not 60%, not 70%, less than 50%. You could literally flip a coin and do just as well. And here's the thing that makes this shocking. These programs were short. We're talking single files, under 400 lines of code. Not giant production code bases, just small, self-contained C programs. So, AWS researchers decided to investigate why. Let's dig into their paper, look at who failed, why they failed, and check out a surprisingly cheap fix that changed everything.
Okay, let's dive into this. Section 1. The AI code illusion. Low-level C code is unforgiving and doesn't stop you from doing dangerous things, which is exactly why AWS researchers pulled 500 tasks from the SVComp 2025 competition. They perfectly balanced these tasks 50-50 between safe and buggy, so the models couldn't just guess safe to get a good score.
So, let's break down this dramatic scoreboard. When you look at the safe programs, the models look absolutely incredible. Claude Opus leads the pack with an impressive 98.3% accuracy, and most of the others are comfortably sitting in the 90s. But look what happens when we switch over to programs with actual violations, real bugs they absolutely need to catch. Claude Opus 4.7 holds up okay at 92%, but then the floor just completely falls out. Massive giants like Qwen 3-coder 48B drop to 74.8%, and Mistral Large 3, which is a titan with 675 billion parameters, collapses all the way down to a coin toss at 50.2%.
And this brilliantly illustrates the core problem we're dealing with here. Scale is just not the answer. Check out this reversal graphic. We have a 675 billion parameter model essentially flipping a coin at 50.2% on actual bugs, right? But it gets beaten by a model a fraction of its size. GPT-OSS is just 20 billion parameters, yet it scored 84.1%. So simply making a model bigger does not magically improve its verification ability. There is no clean correlation there. Something else entirely is going on. And honestly, it gets even worse the longer the code gets. Notice this length cliff. For buggy programs, the accuracy doesn't just slowly decline, it totally drops off a cliff. For example, the Qwen 3-32B model started out super strong, hitting a 90% accuracy on programs under 25 lines. But the second those files grew to just 100 to 200 lines long, damn, accuracy plummeted to a disastrous 32.1%. And keep in mind, this benchmark caps out at 400 lines. If they're failing this hard at 100 lines, imagine what happens in a real-world 10,000-line codebase.
Section 2. Dissecting the failures. So, it's time for an autopsy. The researchers used Claude Opus to categorize over 1,000 false negatives to find out exactly why these models missed the bugs.
Now, what's really interesting about this slide is the breakdown of these failures. 44% were missed edge cases. Basically, the model just didn't consider the specific input that would trigger the bug. But I really want to draw your attention heavily to the 27% categorized as rationalization. This is wild. In over a quarter of these failures, the model actually found the bug, identified the mechanism perfectly, and then somehow convinced itself that it wasn't a problem. Let me give you a perfect specific example of that rationalization in action. A model was analyzing a program with a 40-byte struct, but the code was writing 41 bytes into it. That is a classic buffer overflow, and the model noticed it. It correctly computed that the sizes didn't match, but instead of flagging the bug, it output this exact quote. This is acceptable because the memory is still within the stack. No way, right? It wasn't hallucinating. It just confidently talked itself out of flogging a formal bug by relying on practical, runtime reasoning instead of strictly applying the mathematical property it was supposed to check.
Then you have cases of outright termination confusion. Let's walk through this slow-motion loop of unsigned integer wrapping. You start with an odd unsigned integer, like 1. Then you subtract 2. Well, unsigned integers can't go negative, so it silently wraps around to over 4.2 billion, creating an infinite loop of odd numbers. Mistral 675B looked at this, realized it would wrap, but completely failed its termination logic by assuming that repeatedly subtracting 2 from an odd number would eventually reach 0. It spat out a highly confident explanation that was mathematically 100% wrong.
Section 3. Enters symbolic execution. So, how do we fix this reasoning gap? Well, researchers found a mathematical silver bullet. Not fine-tuning, not prompt engineering, but using Soteria, an open-source symbolic execution engine from Imperial College London and Amazon.
To really grasp why Soteria is so powerful, we need to contrast concrete testing with symbolic execution. Normal testing means running a program on specific inputs, say checking if an input of 42 breaks it, but you can't test infinity. Symbolic execution takes a totally different approach. It explores every mathematical path simultaneously rather than just checking random specific inputs. It mathematically determines what inputs trigger what behavior. It doesn't just say input 42 worked, it says for all even values it terminates. For all odd values it loops forever. It is exhaustive.
Let's move to and see how this builds in Section 4, the superadditive fix. Researchers ran Soteria on 1 million open-source C files to generate 34,000 usable traces, which they'd use for the continued pre-training of the Qwen 3.8b model. But the massive breakthrough came when they filtered that data down to just 3,208 manifest bug traces. These are specific traces where Soteria mathematically proved a violation occurs on all feasible inputs. Training the model on just these 3,208 specific examples took only 10 minutes on 8 GPUs. That is a phenomenally tiny intervention.
So the crucial point is this super additive effect. If you just turn on chain of thought thinking without retraining, performance actually drops by 1.4%. If you just pre-train on the bug traces without thinking, you get a 7.3% bump. But combine them together, accuracy jumps an incredible 17.9 percentage points, going straight from 49.4% to 67.3%. It's crazy. The pre-training teaches the model what to look for, and the chain of thought gives it the computational budget to actually go out and look for it.
But format is absolutely everything. Soteria outputs its traces in a structured HTML format, and that format was literally load-bearing. When the researchers stripped the traces down to plain text, accuracy collapsed to 33.2%. And when they asked an LLM to informally summarize the trace into natural language, it plummeted even further to 25.2%. The structured format of the raw tool output was essential for the model to actually understand the logic.
Section 5, Beyond Memory Safety. And this is where we look at the bigger picture. The model wasn't just memorizing memory safety bugs, it was actually acquiring a generalized pattern of formal mathematical verification reasoning.
Just look at these incredible generalization stats. Soteria's traces only outputted data from memory safety and overflow, but despite never seeing a single trace proving termination or analyzing a data race, the model drastically improved across the board. It jumped 12% on termination, a massive 24% on data races, and 16.5% on reachability. It basically learned how to systematically track state and consider adversarial inputs, and then it applied those exact skills to completely unchecked properties. That is a real game changer.
When we say AI can read code, what we usually mean is that it can pattern match code. It knows what code looks like, it can predict what comes next, it can explain what a function does when the pattern is familiar. What this paper measures is something harder. Can it understand what code does? Not on the common path, on the adversarial path, on the input that breaks the assumption, on the edge that nobody tested. And the answer right now is sometimes. Better than chance for most models, much worse than needed for most use cases. The fix, or at least a meaningful part of a fix, is to teach models the language that formal tools already speak. Traces of symbolic execution, maps of the paths that break things. 3,208 examples. 10 minutes, 17 percentage points. That's not a solution, but it's a signal. It leaves us with a massive question. If just 10 minutes of mathematical reasoning can cause a leap this big, what happens when we finally teach AI to stop just guessing at code and start proving it?